Hi, my name's Bob Greenyer and I'm a volunteer with the Martin Fleischmann Memorial Project. So thank you for waiting. Unfortunately, I had an issue with my camera and so I've had to switch to backup cameras. Sorry about that. Anyway, I think this should go fairly smoothly from now, although I'm a bit flustered because that didn't go so as much as I'd like it. But can people let me know if they can see everything at this stage? That would be useful. You can hear. Okay, all right. Sorry if it's a little bit out of sync. But anyway, we will see. I think I can put the brightness up on here. All right, good. All right. I think maybe some lovely Microsoft thing had updated stuff and it all went awry. Anyway, hi Dan, hi Elias, hi Gordon, hi Corky, hi Alan, I understand you're in the house. Great, brilliant. Okay, so yeah, it was a bit of a shocker. I don't know quite what happened there. At one point I thought I lost all my USB ports on my streaming computer. So that doesn't appear to be the case after a reset, but something was missing. Okay, hi Artifact and Glass Chappie and Carl. Great to have you with me. Right, this is actually the presentation that I wanted to share on Sunday, but I threw in the electron scavengers because it seemed right to do it that time. And I'm glad I didn't share it on Sunday, and this is often the way. Some serendipitous moment happened on Monday, and I got some new material sent to my inbox that actually led me to make what I hope is a much better presentation for you today. But essentially last week, I don't know if people were aware, but there was a ARPA-E meeting in the US. And one of the people there, which were one of the leading global players in LENA that were presenting there, was Clean Planet. And actually, Clean Planet, it is out of Tohoku University, but it involved a lot of Japanese people. And in fact, over the course of the last few days, I realized just how integrated the Japanese researchers are in a way that I'd never really clocked before. So I've talked much about the integration within the Russian, the Soviet sort of field, the cold nuclear transmutation and ball lightning. But actually, it is quite clear, and I think you'll probably come to the same conclusion, that there is a lot of cross-pollination going on in Japan. And in fact, they hold their own Japanese cold fusion conferences every year, over and above the ones that are held internationally. And that is true of also the Russians with their conferences. So, it kind of made me think that until this European project has come about with the European funding, there hasn't really been that much coordination in the West outside of the initial burst after Pons and Fleischmann. And when you think about it, really there was a lot of attempts to, maybe some better than others, to attempt to replicate the original findings of Pons and Fleischmann. And then from that point onwards, and I don't know of many replications until we actually attempted to replicate Francesco Celani in late 2012, which we apparently succeeded. And I think the next one that was replicated was Technova's replication of Mitsubishi, or vice versa, of the work of Iwamura in this calcium oxide layers with palladium and then whatever element that they wanted to see if it would transmute, and some deuterium diffusion through that. And we're going to actually touch a little bit on that today in terms of, you can see that name pop up again. It's a very principal, Iwamura is a very principal figure in the field. But what surprised me as I was going through this exercise, which I'm going to lead you through today, is that there was also topics that were being discussed that connect through to Matsumoto's work and to the work of Brillouin. Now, I have a lot of respect for Robert Goddess. He came onto the scene after thinking, well, it's not happened, let's give it a go. And he we haven't always seen eye to eye, but then my eye has been changing as I've been getting more information. And that is also something that Matsumoto did. But you also have an initial hunch of what must be going on. And I think what it comes down to is the cover slide that I have for this presentation is here. And you can see that I've called it What Do Takaaki Matsumoto, Brillouin Energy Corporation and Clean Planet Have in Common? So as I was saying when you were patiently waiting for me, down the bottom here I've added all these links in, and I've got the Japanese one, the English one that I painstakingly translated last Friday, then the Japanese poster, and then my translation of that Japanese poster. And this is the sort of process that I led through, that I went through when I was doing my research since last Thursday. And I think I've learnt quite a bit, and hopefully I can get through some of my learning to you. But what do they have in common? Well, they're all claiming to observe the fusion, effectively, of 4 protons to 1 for helium. Or at least that's what it would seem. So we're going to go through where I started, which was with this reference here. And if I click on that reference, it should, in fact, I'm going to pull this out into a different window. So just give me a second here. I'm going to pull this out to a different window, and then we're not doubling up on what we're looking at. And I'm going to throw in, I've got my memory stick over there. So, so we're going to click on this first reference here. And you can do this with me. So this is on X-Tech, and it is on a Japanese news site. And for those that don't read Japanese, I painstakingly did a translation of this, which you can get access to here. And if you click on that, you can follow along with me, hopefully. And this is boilers using nuclear fusion and so forth. So I'm going to... hopefully this will do this, and it's downloading it. I still have people in the office shared space here. So what I'm going to do is I'm going to actually pull this into a different application, my copy, so that I can go through it with you and pull out some things that are relevant to discuss today. So just give me a second with that. If you have any questions as we go, drop them into the chat and I will endeavour to answer them. So let me find where I want to do this. Now, I do apologise. Nearing the end of this presentation, I'm going to show a few equations, and I know I don't want to do that, but they're rather simple, and I think it'll help explain the concept. And I think you can, if you remember the dineutron conversations that we've had in recent weeks, I want to kind of bring that in with respect to itonic clusters and how these fit into these other theories of how the 4 helium is produced. Now, why would people think that 4 helium was something that was being produced in these systems? It's it's quite reasonable, because that is what was being claimed by Pons and Fleischmann, and so everyone tried to explain these miracles of there being fusion, and then there being where's the helium and where's the missing tritium and neutrons, which don't seem to be coming out in as abundance, and where is also the gamma rays that you should be seeing. So a lot of people have done a lot of work to try and explain these miracles, supposedly, that happened in cold fusion. So we're going to go through the basic work of the boiler first. So let me find that one here. And it's not that one I want. Okay. Okay, so I think I have what I want to share with you here now. Okay. So a boiler by nuclear fusion, heat is put into practical use, heat is taken out by metal laminated chip. I've only corrected some of the translation errors in this where it was just absolute nonsense. So sometimes there'll be grammatical errors here. But anyway, jointly developed by Muraco Limited and Clean Planet, commercialized in 2023. So that's their target, is to have a commercial reactor in 2023. And this is on the 12th of October 2021. So it's practically hot off the press. And this is written by Kenjo Kaneko, Nikkei BP Research Institute, Clean Tech Lab. Okay, so nickel and copper laminated chips. Now, you might know that the Celani wire is made from nickel and copper. Anyway, these are laminated chips. Condensed nuclear reactions were once called cold fusion. Researchers at the University of Utah announced this phenomenon in 1989, and it was the limelight worldwide. In response to this report, as a result of conducting additional tests all at once, major research institutes, including Japan, announced negative views. A report from the University of Utah was that when the palladium electrode was immersed in heavy water and electricity applied, excess heat that could not be explained by chemical reaction was observed. However, in additional tests by many researchers, the phenomenon itself is poorly reproducible, and it has even come to be seen as similar science. Now, you could have this introduction to millions and millions of cold fusion any journalist will write something that starts off a bit like that. And so this is just another one doing the same thing. But anyway, however, some researchers continued their research steadily, and in addition to the electrode method, phenomena such as heat generation due to deuterium storage in palladium nanoparticles and nuclear conversion due to permeation of deuterium gas into a palladium thin film were reported. So this is what we're talking about with Iwamura. The reproducibility of these phenomena has gradually increased. Since around 2010, venture companies aiming to use the energy have been spawned one after another in the United States, Italy, Israel, and so on. In the United States, major IT companies such as Google are also entering the market. Clean Planet is a venture company established in 2012 based on the Condensed Nuclear Reaction Research Division in the Electronic Photophysics Research Center of the same university, which was established jointly with Tohoku University in 2015. So ICCF 20, I think it was ICCF 20, was held in Tohoku University and a laboratory in Kawasaki City. We are working on the practical application of quantum hydrogen energy. I quite like the idea of that, because the MFMP is a project of quantum heat, so I fully approve of their idea, quantum hydrogen energy. At Tohoku University, he is in charge of basic research led by Professor Yasuhiro Iwamura. So this is the guy that I'm talking about, and when they are referring to these palladium thin film, it's talking about the Yasuhiro Iwamura professor, and this is one of the justifications in retrospect for me thinking that the calcium oxide observed transmutations were real in the HHO exposure in our recent testings as a view to trying to fix Fukushima. Anyway, who achieved results in the same field while enrolled at Mitsubishi Heavy Industries. So he did these tests, and it was Teknova from Toyota, a division of Toyota, I think, that replicated them. So that was the major second sort of replication outside of those initial furious replications that were going on. Now I'm glad to see that there are a lot of independent labs that are attempting replications of things like the lattice energy converter, and there have been attempts to replicate the Parkhomov reactors over the years, and Alan Goldwater and with the MFP did some stunning attempts at that. Of course, his work, Parkhomov's, ended up mostly being actually just a nickel hydrogen system because the lithium got in the way of the reaction. But anyway, and the laboratory at Kawasaki City is continuing development for practical use. The reproducibility of the exothermic phenomenon has already been secured at 100%. Now, this is huge news to me. This is huge news because they are saying this works absolutely every time. And the research subject has shifted to quantitative reproducibility, i.e. to make it work at a high level, I guess. So, focusing on these research results, Mitsubishi Estate invested in Clean Planet in 2019, and Mura Co. Limited invested in Clean Planet in May of the same year. Since then, research has progressed steadily towards practical use. So this time we have decided to start full-scale joint development with Mura Co. Limited regarding its application to industrial boilers. A prototype will be produced in next year, and it will be commercialized in 2023. This is really confident. We have here some claim about 100% reproducibility, that they've just got to get the power levels up, I suggest that means, and that they're looking to produce a commercial prototype and deliver a commercial product in 2023. This is really, really exciting news. What should be noted in the research results of Clean Planet is that 100% reproducibility is ensured by the heat generated in the reaction system, mainly composed of nickel, copper, and light hydrogen, which are relatively inexpensive, obviously in contrast to the high expense of the palladium deuterium system. Okay. Specifically, when a chip heating element in which 14 nanometer nickel and 2 nanometer copper are laminated in multiple stages is placed in a vacuum state, light hydrogen is sealed and heated. Heat exceeding the input energy is released for a long period of time. This works, basically. The calorific value cannot be explained by chemical reaction. The crystal structure of the chip metal has a lattice defects in some places, and multiple hydrogen atoms get stuck. Now, lattice defects, well, we've seen things occurring in crystal grain boundaries in many people's work, but principally by Matsumoto and also in our NOVA experiments. But this is saying lattice defects, so where crystals are growing and you've not got a perfect crystal lattice. So it's kind of the same thing, not necessarily a crystal boundary, but when you get some sort of imperfections in the lattice. And multiple hydrogen atoms get stuck in the defect and approach each other, leading to fusion of nuclei by condensation. Leading to the fusion of nuclei by condensation. At that time, the mass defect is released as heat. And by now, you should all know what I mean by that. So apparently, this is the heat generating element. It looks like it's in some sort of a container here, and it's nickel and copper laminations. Okay. So that is that. Right. The heat generation and energy density is 1,000 times. The commercialization of heating device that uses heat from transmutation is imminent. On September the 28th, new energy-related venture Clean Planet and Mura Co. Limited, a major boiler equipment company. So this is actually a company that makes boilers. I've teamed up with Clean Planet. So it's actually, they have a path to market. Announced that they have signed a joint development contract for an industrial boiler that uses quantum hydrogen energy. Quantum hydrogen energy is a technology that utilizes the enormous amount of heat released when hydrogen atoms fuse, and is a term uniquely used by Clean Planet. The principle of generating energy is based on nuclear fusion, which is the same as thermonuclear fusion experimental reactor ITER that is being promoted in international frameworks such as Japan, the United States, and Europe. Theoretically, the exothermic energy density of a nuclear fusion reaction is more than 1,000 times, I should imagine it's even more than that, of gasoline. It's like 1,000,000 times. I think this should be 1,000,000 actually, but anyway, let's call it 1,000, that's good, of gasoline combustion chemical reaction. And if it can be put into practical use, humankind may be able to obtain an order of magnitude more energy. Well, I would argue that is a lot more than an order of magnitude more energy. That's at least two or three orders of magnitude, isn't it? The difference between quantum hydrogen energy and thermonuclear fusion reactors is that while ITER requires a huge facility to magnetically confine the high temperature plasma state of 100 million degrees Celsius, Clean Planet works on quantum hydrogen energy. Okay, we get the point. The point is that it can be a distributed energy source that can be installed in factories, etc., because it induces nuclear fusion at significantly lower temperatures such as 1,000 degrees or less. It is great. You can make small units that can be delivered everywhere. Nuclei are attracted and fused by nuclear force. Okay, this must be the strong nuclear force, I would say, when they approach a certain short distance. Yes, so when it gets into a certain short distance, and we'll see this in the later papers that I'm going to go through. But in order for the nuclei of some charge, the same charge to approach this distance, it is necessary to overcome the repulsive Coulomb repulsive force. Okay, a thermonuclear fusion reactor requires a high temperature of 100 million degrees Celsius for that purpose. That's just smashing the elements together. On the other hand, in quantum hydrogen energy, nuclear fusion is induced by occluding hydrogen. Now, there's only 2 times that I've come across the word occluding in this field. And it is once when I was looking at I think it's the 1876 maybe, or 1873 paper of Thomas Graham FRS, Fellow of the Royal Society, when he was showing how much hydrogen, and there wasn't any deuterium or tritium known at that point, so it was just hydrogen in his view, would occlude into metals. He actually defined that ratio for palladium and other metals, but also that palladium has the highest potential for occluding hydrogen, or that's absorbing, that's into the metal lattice. And he called it occluding. And the Japanese tend to use this word occluding also. Occluding hydrogen in minute metal particles and stimulating them under certain conditions. These phenomena are called condensation-type nuclear reactions. New thermal reactions between metallic hydrogen and low-energy nuclear reactions among researchers, and research has become active in each country. Now, when I saw, and I was doing this translation, I saw it last Thursday, and I was doing this translation last Friday, I was disappointed that there was not enough resolution in these images to be able to see what was going on, and I couldn't really tell what was happening because, yeah, it's just a bunch of images. But I can see that there's hydrogen coming in here, and it says H2, so I guess this is, 2 protium in a molecule of H2, and they're going into this metal nanoparticle, and they're fusing, and things with a cluster size of 4 are coming out. And since we know that quadronium doesn't exist for more than an extremely short period of time, one can assume that it is helium. So that's the best I can do for you until later on in this presentation. Anyway, that's the principle. And so they have a picture of the reactor here, the test reactor, laboratory equipment in Kawasaki. Every time I hear Kawasaki, I think of a really fast motorbike, but anyway, that's just me. Leverage effect of renewable hydrogen. According to the equipment in the laboratory in Kawasaki City, once hydrogen is filled in the chip and heated, it will continue to generate heat that exceeds the input energy for about 120 days. That's really nice, isn't it? That's nice. I like that. At that time, the COP, coefficient of performance, indicates how many times the heat energy input over consumed energy can be obtained, exceeds 12, a COP of 12. Since the COP of general heat pump water is around 3, it is expected to be able to generate an order of magnitude of heat. Okay, so there we go. And we're nearly done on this, and then we're going to start finding out how this actually works according to the Japanese researchers. A major feature of this nuclear fusion by a condensed nuclear reaction is that the thermonuclear fusion reactor does not emit radiation. There we go. That's one of the miracles that you need to get rid of, as such as neutron rays and beta rays. No radiation was observed in the Clean Planet fusion system. The company says that it will first collaborate with Mura Co. Limited to commercialize a boiler that generates high temperature steam used in the drying process of factories. So it's going to go into commercial use in factories. The higher the input temperature of the heating element, the more active the reaction. Therefore, the waste heat of about 200 degrees, which cannot be used up in the factory, is continuously input to the inlet temperature. That's really useful. So after a short while, the 200 degree waste heat gets recycled, and it just has to elevate that to 500 degrees, I guess. To the inlet temperature, and the outlet temperature is raised to about 500 degrees, it is assumed. And so they have this sort of reaction here. They've got 2 nanometers of copper. They've got nickel, 14 nanometers. So these are really thin layers, and the hydrogen is doing its business through there, and it's producing our heat. Mr. Mito Endo, CIO, Chief Innovation Officer of Clean Planet, said at present there are cases where the measured calorific value is 2 to 3 times larger than expected value. So the expected value maybe is what it said down here somewhere, and it said 12 times or whatever it was. Yeah, so 12 times. But here he's saying calorific value is 2 to 3 times larger than the expected value, and quantitative reproducibility is still an issue. Okay, so we've had all our it works. We're going to deliver a product in a test product in next year, and we're going to deliver a commercial product the year after. But here it's saying a quantitative reproducibility is still an issue, i.e. this thing sometimes runs away with itself, is what I'm reading here. People might have a different interpretation of this. We would like to continue to improve it over the next 2 years and commercialize it after sufficiently improving the accuracy of temperature control. Okay, so whatever they're using to stimulate this, which is presumably the input heat, if that's all it's doing, then they do have some times when it goes a little bit over. Now, when you understand that the technology that or their approach to the understanding of how it's occurring, you couldn't really imagine it doing this overheating process. But when you can understand that a coherent system can become a much larger thing, then you could have a little bit of a runaway that can damage the material. But anyway, it says beyond that, we are imagining the expansion of industrial applications, consumer applications, and applications to power generation systems. It is said that it is possible to generate a high temperature of nearly 1000 degrees by stacking multiple heat generating elements. In the future, we can expect application to various high temperature processes that are difficult to electrify in the manufacturing process, said Mr. Endo. However, when the temperature exceeds 1200 degrees, the nickel melts and the layer structure of the device collapses. So the reaction stops there. From a different point of view, even if the temperature of the element rises sharply due to heat exchange problem, it will stop when it reaches 1200 degrees Celsius, so thermal runaway will not occur. Okay, so basically saying the system requires this metal lattice to be in place for it to work, but if there is a runaway, and it would suggest here that they are having problems which they need to fix with runaways from time to time, that it will run away and fail safe because the nanostructures that are here will be damaged. Now, I have a couple of issues with this, and the first one is that they're saying the limit is 1200 degrees. Well, actually, the copper here will melt at 1085 degrees, so that is an issue. But also, if they actually do have nanostructures, and if you look at this image over here, it looks a bit powdery. And that might just be the image quality, but one can imagine that they are sputtering or something on there. And if there are nanostructures in these layers, then I would suggest that this is going to fail at a much lower temperature. And from our experience, this fails at about 400 to 450 degrees centigrade. So what happens is you get these little, very much smaller structures in there that have a sort of Maxwell's demon. They get a little bit more energy localization, and I've talked about Messiats and the ecton explosions from those. And you can imagine if you had 2 points of nanostructures close to each other, they would sinter together, and then you start to lose the nanostructure type nature of it. And this, from my experience, starts occurring at 450, 500 degrees centigrade on even the nanostructure points of the PNK02 nickel we had from Parkhomov and some of the other fine nickel structures that we had. And at one point we actually did purchase some nano nickel, and it's quite easy to sinter that into a block. Anyway, so I suspect that I think what's going on here is that this guy, Mr. Endo, and I apologize if he knows much more, but he's the chief innovation officer, so he's kind of like maybe thinking on a sort of what can we do if we can achieve something. I don't think I get the impression that he needs to think a little bit more about the material science to understand that he's probably not going to achieve getting to 1200 degrees when he's got nanostructures and copper. It's just, in my view, it's just not going to happen. So the first part of this document looks really, really exciting. I pretty much am certain that they're getting 100% repeatability. I think in the low temperature ranges, that's realizable. I think that if they're cycling between 200 degrees and say 450 degrees, they are going through the nickel Curie point. And therefore, I believe they will be able to maintain this excess heat in the processes which I've discussed in previous presentations. But I can't really believe. I think there's some sort of clarification that they need to make here. Why they think their copper can go above 1085 degrees and why their nanostructures they believe can exceed 450 to 500 degrees. I'm not convinced at this point, and that's always a shame when I see something that is published, and it could be maybe the excitement of the journalist and they misinterpreted a couple of things and it was just in the writing it came out like this. I don't know. So I think that needs to be clarified with Mura and with Iwamura and so forth, if that's actually the case. In addition, for consuming heating applications, the type that can self-sustain heat without applying additional heat is suitable by devising a heat-insulating structure. For example, by making the chip into a sheet and making it a rolling paper structure like a capacitor, the heat generation temperature can easily rise, and it is possible that the heat can be self-sustaining and maintain a constant heat generation for a long period of time, said Mr. Endo. So, again, I'm seeing this kind of this person, Mr. Endo, kind of is like someone who's like thinking ahead of what it might be possible. And yes, this is something that, you know, if it's purely a heat-driven process, then you know that could well be the case, because when you see what we're going to discuss later, it is kind of thermal vibrations that are the type of vibrations that are needed to stimulate this coherent condensation process. So you can understand how this would lead to some level of how should we put it, self-sustaining. Okay, the nano-level laminated structure of heat-generating elements can make use of thin film technology that is the strength of Japanese manufacturing industry. No one could argue against that. By partnering with a company with such know-how, we believe that it will be easy to increase the area of the chip and make it into a sheet. The range of applications will also expand. So the implications I'm getting, the vibe that I'm getting from this is that this is the size of the chip. I mean, there's no scale on here, but it doesn't look like it's very big. And so, you know, that they're arguing that once they've got everything set up, then they will be able to make the device larger. When deploying to a power generation system, it is said that it is imagining a combination with a steam turbine generator. A compact structure using thermoelectric elements is possible, but if power generation of efficiency is emphasized, the Rankine cycle, which converts heat into steam and turns a generator, is considered to be advantageous. Right, so someone who went or was party to the ARPA-E meeting said that I think that they were presenting something that was in the around about the kilowatt generation level, and that is around about the 1 to 1/2 of the level that was generated by the Parkhomov 225-day reactor. I think there was like a kilowatt going in, and at one point it was generating 3.7 kilowatts or something of heat. And that is a nickel hydrogen system alone. But I believe, as I said before, that the active agent is going into the tungsten heating coil, and that is producing power as well. So it's on the same order as the Parkhomov technology. But, you can argue, is one simpler than the other? I don't know. Probably not. Okay, quantum hydrogen energy will be carbon-free system. Yes, great. That does not emit CO2. Great. If hydrogen, which is a fuel, is produced with renewable energy, currently a fuel cell system is used to convert hydrogen derived from renewable energy into electricity. But in that case, the power generation efficiency is around 50%, which is a large loss. With quantum hydrogen energy, the amount of electricity that can be produced from the same amount of hydrogen, including the loss due to the Rankine cycle, can reach several times more than that of fuel cells. The leverage effect works on energy, and as a result, the development capacity of renewable energy can be reduced. So anyone who's got a renewable energy business, it's time to start waking up. Hideko Yoshino, president of Clean Planet, said, at present we are at the forefront of the commercialization of quantum hydrogen energy and have already obtained patents in 21 countries. There is also a move to rapidly expand investment in it, and we would like to continue collaboration with energy-related companies that have know-how to speed up development and expand into various applications. So 21 countries, they are saying they've obtained, they're not applied for, they have obtained, and of course they're going to be a leader in quantum hydrogen energy because that is their own term. Okay, so what is quantum hydrogen energy? Well, that is where you will need to, I'm going to quit that now, we'll go to the second thing. So that is that first press release there. And the second one is this poster, and this is actually from 2018 here. And I've got the Japanese link here, but what I've done is I have translated that. So we've got that here, and maybe we can look at that in the web browser here, and maybe that's just a faster way of doing it. No, maybe it's not. So I'm going to look at this one here, probably. I'm going to do it here. Okay, well, is it going to be faster? I don't know. Maybe. Let's see. So this is my translation. You can go and get this translation as well. Is it going to? No, it's not going to look good. So let me do this. Sometimes you're just going to use the right tool. Okay. Okay, so the great thing about what I'm looking at here is that I see this graph down the bottom here, this image that I saw in the previous thing, that I couldn't see the the things clearly in the previous PDF. So I'm going to go like this, and I'm going to go like this. Okay, right. Okay. So this is my translation. Again, I painstakingly translated this for you, so you don't have to. New thermal reaction between metallic hydrogen, ultra high energy density, cheap, clean, dream energy. Okay, so this actually is from 2018, and it is produced by Teknova. And the interesting thing is that Teknova is the division, I understand, of Toyota that replicated the Mitsubishi work that was being done by Iwamura. And so you can see how these things are all connected. And now they're talking about this, and this was part of, if you can look down the bottom here, it says, this result was obtained as a result of the project of implementation of new energy industrial technology development, NEDO, a national research and development corporation. So this is Japan getting together a lot of its technologists to actually deliver a practical solution. And one could argue that maybe Fukushima aided the desire to bring this about. But anyway, let's read it. Product tech name, introducing the results of the Energy Ring program phenomenon analysis and control technology for the new thermal reactions between metallic hydrogen. So this is the poster overview. This is a poster. We would like to introduce the results obtained in the energy and environment new technology leading program phenomena, blah, 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 between 2015 and 2017. New thermal reaction between metallic hydrogen is a special reaction that occurs between nanometal and hydrogen and generates more than 10,000 times, this is more like it, 10,000 times the thermal energy of a chemical reaction. So this is definitely more than 1,000, so this is 4 orders of magnitude. Core technology or patent information. Long-term continuous heat generation. Yes, we like that. When hydrogen is occluded, there's that word again, occluded in nanocomposite metal particles, such as palladium, nickel, and copper nickel, and then the temperature is raised to about 300 degrees C, heat is continuously generated for 1 month or more. And I think they said effectively 3 months in the later announcement, the news article that I've just read. But I've done the translation here, and so I was pretty right. It's hydrogen, H2, protium in the monatomics there, going into, this is our nanometal particle here, and it is storing the hydrogen in there. Then there is this occlusion, so the hydrogen is grouping together into the metal lattice, and in the case of palladium and in the case of nickel, it's face center cubic. The reason you want to use nanometal is because you get these anharmonic oscillations, and also which lead to vast differences in energy in some places, as we observe in the ultra experiment. That's kind of almost like an anharmonic oscillation. There's areas where you get extreme changes from the normal level of energy at a resonant point, and so you have these particles in there. But the reason you want nanoparticles, particularly in the case of nickel, is that, and in both of these things they have nickel. Now, obviously, nickel is magnetic, and they're doing palladium nickel, and I think palladium is paramagnetic and copper is paramagnetic, but nickel is ferromagnetic, as you know, and I've given explanations that none of these guys seem to think about, but anyway, at some point I think they will. But anyway, the nickel is face center cubic, I think, or FCC. I think that's the right, and so is palladium. So these systems, and it'll make sense when you see how this occurs. And so what you can see is that these protium, so these are hydrogen, they're obviously being split apart, and the monoatomics are locating themselves in the regular lattice, and then they are forming into helium, it would appear. So at some point, somehow, 2 of these, of every 4 that are coming together are converting themselves into neutrons. And what that requires, absolutely and certainly, is for an electron to come in and a neutrino. Somehow that's got to occur. But anyway, there we have it. That's our 4 things there. Now, they're not a bit player. If you look down here, they have they've been going since 1978. They've got quite a bit of capital, and they have 35 people. Now, I thought actually, because I've seen them presenting, I thought they were a bigger operation than 35 people, but they have access to incredible technology for doing analysis. And I don't know, because the last time I saw Technova, they had access to a cyclotron, and it's a big thing. Anyway, features points: enormous energy is generated, density of 25 megawatt hours per kilogram or more. Hydrogen is the fuel, which is inexpensive and has no resource restrictions. Does not emit CO2, which is the cause of global warming. Well, yeah, okay, maybe. Okay. Does not emit PM. These are fine particles. I think it should say PM10 is the one, or particles under that size, which are the nasty particles for pollution. fine particulate matter that causes air pollution. And the reaction system is simple and can be reacted with a simple device, or controlled, I guess that means, with a simple device. Expected destinations and merits for consumers, for customers. The new thermal reaction between metallic hydrogen can be applied to various fields as high energy density, low cost, safe, clean power energy, and can be used for not only as a heat source but also as a power source by converting heat into electricity. And they've given all the things you'd want to use it for. Okay, and on this one, they talk about the different people that are involved, and here we go. Nissan Motor Company, National University, Kyushu, Tohoku, Nagoya, National University, Kobe University, Technova here. So yeah, there's a lot of different universities involved in this process. And this was the process that they went through, and this was their R&D, but you've kind of seen the product of the R&D in the presentation I've just gone through here. And this is showing the excess heat period, and here's their reactor as it was back in this 2015 to 2017 period. Summary: install a new high-precision thermal evaluation device and check the accuracy. Conduct joint tests 16 times to confirm the existence of excess heat generation phenomenon and experimental reproducibility. Confirmed an energy density of 10,000 times or more that of existing chemical reactions, which is 3.6 gigawatt hours per kilogram. Confirmation of excess heat generation in DSC measurement. That's the type of calorimeter that they used. Okay, so I guess this is the calorimeter here with a little chip in it, maybe, I don't know. Differential scanning calorimetry, there we go, DSC at Kyushu University. Okay, so that is that one. And so how I got to this actually was I am on ResearchGate and I subscribe to Akito Takahashi's ResearchGate account. And on Monday, I was sent this document by ResearchGate, and it was from October 2021. In fact, it was from, I think, last week, and it might have been some sort of quick paper that was put together in preparation for this meeting that occurred. Okay? So I'm going to go and just get this paper up for you, and then what we're going to do is feed into his theory, and where is it? It is here, I think. No, it's not that. Okay. So basically, this came into my inbox on Monday this week, which was still yesterday, as we are here. MHE, nuclear-like thermal power generation, guiding TSC theory. And I thought to myself, it's probably about time that I found out what TSC theory really was. Anyway, so we'll come back to this because I think it's probably relevant to come back to it at the end. I'm going to go and look at TSC theory, and it is here. Okay. So this is Progress in Condensed Cluster Fusion Theory, and this is from February 2011. Okay. So Akito Takahashi, and when you look at this, in fact, it's relevant to actually look at this from the point of view that it has this diagram. It's not another diagram. It is exactly this diagram. Okay. All right. So this was sent to me on Monday, and it ties into the diagram that you see here and which you see in the other diagram. So you can see how the Japanese are really quite fixed on this kind of understanding. Okay. And to a large part, it comes from this work of Akito Takahashi. Okay, so TSC is the tetrahedral symmetric condensate. TSC is tetrahedral symmetric condensate. Okay, So this is using a tetrahedron, which is, you know, a what is it? Three-sided structure, is it? Three or four-sided? Three-sided pyramid, I guess. And key idea for clustering and dynamic condensation. Final products of 4D fusion, that's 4-deuteron fusion, are mainly 4 helium nuclei with 2 to 5 megaelectron volts main component and 23.8 megaelectron volts minor component. Okay, so basically he complains about these are the 4 miracles. How can a mutual Coulombic repulsion between deuterons be overcome at low deuteron energy so as to attain significant levels of deuteron-related fusion? How can the 4 helium generation channel be predominant, which is one of the miracles of Pons and Fleischmann? How can hard radiations be suppressed? And what kind of environments in condensed matter are conducive to the condensed matter nuclear environment? Okay. So I'm just going to pull out a few things here. This means we need to invent some nuclear process in condensed matter to explain 4 helium production in correlation with excess heat. One simple way is excitation by incident gamma rays with energy more than 20.21 MeV. And this kind of gives me some sort of feeling for the is it the Oppenheimer-Phillips reaction that is being explored by NASA and Global Energy Corporation, and so you get this photon energy absorption, and so maybe he's just discussing that's one way. And then down here it says we need to consider a time-length force exchange boson, the photon for electromagnetic interaction, so that's not going to be very relevant to you guys. Okay. So here we go. This theoretical model treats a process of condensed cluster fusion of multi-body deuteron interactions in condensed matter. So condensed matter, what do I mean by condensed matter in this case? I mean that the matter is not a plasma. It is not... I mean, you can have a dense plasma and it's kind of condensed. But really liquids or solids, or maybe supersolids, if that is a thing. Okay. So here it's talking about a higher phonon excited states. So phonon, what are we talking about here? Well, a phonon is basically like sound, but in this case it's obviously ultrasound. And this vibrates the material, and if you look at this thing here, you have your palladium lattice atoms here in this FCC, I think it is, array, and in there you have this 1-to-1 ratio of deuterium nuclei. So there's a monoatomic deuterium with their electron cloud. And as you do the phonons, you end up with vibration. And so the electron cloud moves over, and you end up with these crossover, and he calls them decluster formation probability will be enhanced around T sites. So this is this area here where you're potentially getting the interaction between the deuterons. Okay, now this is just one layer in the FCC lattice. If you can imagine the layer above this, it's offset by sort of one unit this way and one unit that way, and so you end up with this tetrahedral kind of a structure. So so I guess that's 4. Yeah. So it's like one half of a diamond, I guess. Okay. So where are we? Now the thing is here, it says here that a time window of about 50 femtoseconds was conceived for transient 4D cluster formation with about 10 gigahertz lattice plasma oscillations under D phonon excitation. Now 10 gigahertz, that is, in my view, in the field of microwave, and I'm going to suggest something here, probably at the end, because we can achieve this by using as I suggested when I visited the Hutchison lab, I was referring to work that was conducted in the 1950s and published in the late 1950s, early 1960s. I think it was at Manchester University. I've talked about it before, where you put a piezo material, in this case they used quartz, and they excited it with a magnetron. and that was up to this sort of 10 gigahertz or whatever it is. Yeah, you'll know about microwaves in your phone at 2.45 gigahertz. Or in your microwave at the same frequency, or maybe 5G, which is 5 gigahertz in your 5G microwaves in your 5G Wi-Fi in your house. But this is 10 gigahertz, so that is half again the length of cycle. The energy goes up, but this actually gets to the level of the vibration is the interatomic distance, and that's exactly what it says in this. I think it's in New Scientist. I've published this before. Paper from 1963, and all you need to do is put a piezo material on the outside. So I was suggesting that John Hutchison, maybe if you had some aluminium nitride on the outside of your aluminium bar, that if that got excited by microwaves, that would transduct the electromagnetic waves into phonons at the frequency of the microwave. And so you could use zinc oxide or something like that, or you could use inclusions of silicon dioxide. And I'm going to talk about that a little bit at the end with respect to Celani wire. But anyway, so essentially these vibrate, and it's relatively simple to grasp in a minute. So we're going to get here. Don't worry too much about these terms. It's going to be visual in a second. So you've got electronic quasi-particle expansion theory and tetrahedral symmetric condensate, TSC. There we proposed a multi-body deuteron fusion process by formation of tetrahedral symmetric condensates, TSCs, and octahedral symmetric condensates, OSCs. Okay? And transient clusters of tetrahedral symmetric condensates can be formed with certain probabilities by excitation with external UV or EUV laser. This is what we were talking about in the last presentation. UV or EUV laser. Obviously, Low suggested you could stimulate coherence in deuterons using a laser in 1973. And what you're doing here is you're getting the deuterons very, very close together, and then you're exciting them. Now, I'm suggesting you can excite them potentially by using a piezo coating and creating microwave interactions. Now, why am I saying that? Sorry, you can't see me. I'm talking about here. I'm only reading what's on the page. So here, and it's saying with an external UV or EUV laser. The reason I'm saying microwaves can do this and in the palladium deuterium system is because that is exactly what the late Norris Peary did of Peary fusion. And you can go and hear my interview with him in early 2017 on the SoundCloud for the MFMP. And on there, he's saying how he loaded palladium rods electrolytically with deuterium. And then he put them in a microwave chamber with an electrostatic field and then hit them with very small amounts of milliseconds of 2.45 gigahertz microwaves. And that was sufficient to stimulate them. Now, in that case, you could argue that maybe the hydrogen in there, if there's any bonds or whatever, that might be vibrating at that frequency. So it might be doing it anyway just because of the nature of hydrogen or whatever. I don't know, or water in the environment producing some sort of resonance with the microwave. But anyway, that's what he was doing, and he was creating, he said, every element in the periodic table. So there is a history of using microwaves, and I'm going to talk about a little bit more of that in the end, but let's just clarify what's going on here. Okay, so in the EQPET models, and what is that again? It is electronic quasi-particle expansion theory. Oh God, it'll make sense in a minute, honest. We assume that a total of 4 deuteron wave functions can be expanded by a linear combination of partial wave functions of DDE star type molecules with regular electron states E11 and electronic quasi-particle states such as E star and Cooper pair, which is a Cooper pair, and E star 4, which is a quadruplet. What are we talking about here? Well, an electron state 1,1 is 1 this is literally 1 electron. This is 2 electrons as a Cooper pair, right? And this is 4 electrons as a quadruplet. Now, I have argued that what Clean Planet were doing in their patents, they were talking about many times. If you go and look at the Clean Planet patents, they're talking about heavy electrons. What are heavy electrons? Well, I have argued for a very long time that they are just condensates of normal electrons, where initially 2 coming together to form a boson is a Cooper pair, and then beyond that it's clusters of those bosons of electrons. And guess what? That is exactly what they are saying here. A quasi-particle, this is the boson, which is a Cooper pair, and this is 2 Cooper pairs coming together, and so on. These are exactly what I was hypothesizing without ever reading this, that what they meant in their patent as heavy electrons is exactly what they are. And in fact, in Piantelli's work, he is actually calling the H minus, it's actually a proton with 2 electrons or whatever. So the Cooper pairs, and I think Norris Peary called it a negaton, and I think Santilli called it a magnon, and Reginald B. Little called it E minus P E minus. Okay, so a lot of people had the same idea, okay, but what they're saying is that these come together to form larger and larger coherent structures, okay. So these are just, it's not so useful. So this, I think, is the money shot to grasp what we are talking about here. So I'm going to take a little bit of a time with this. So what does it say? Illustration of initially formed 4-deuteron TSC around some T sites. So we've identified that the T sites are here. They are the boundary in between 2, and in fact, because of the location of the in the layers above and below of the palladium atoms, you know, there's going to be multiple doing this. But anyway, this is the T site here, is what we're referring to here. Okay, so under D phonon excitation, 4 centers of electron waves are drawn with E minus and will form a tetrahedra by an exchange interaction of 1s electron from D plus and 5s or 5f electrons from palladium minus states. Okay, so here we have, I hope this comes out, you have 1 palladium here, 1 palladium here. So I was kind of right, it is a tetrahedra, it's like a three-sided thing with a peak here. So it's a 4-sided polygon with each one having 3 vertices. Okay, so this is our 3-sided pyramid. If that's the right 4-sided pyramid, but 3 God, you know what I mean, it's got four vertices. Okay. No, yeah, it's got 4 vertices and 1 2 3 4 polygons. Okay, I'll do. Okay, it would be easier if I did this in the middle of the day. Okay, so we have an E minus with the spin up here on this one, and we have a E minus with the spin down. And over here we have an E minus with the spin down, and over here we have an E minus with the spin up. So this can form 1 Cooper pair here, and this can form another Cooper pair. So this is 2 Cooper pairs of electrons that form this box, and they interact and grab, because these are the center of the electrons. The actual field is much larger, and so that they are interacting. So that whole thing is effectively forcing these deuterons into the central area, and so that is kind of where it's coming from. So they're coming from these O sites, the spaces, and they're coming to the T site. Does that make sense? Does that make sense? Anyone, let me know if that makes sense. So subsequently, we have considered that squeezing motion. Squeezing. This is putting something into a small box. Yeah? And remember, what we are looking at here is tetrahedral symmetric condensates. Okay? So, subsequently, we have considered the squeezing motion of tetrahedral symmetric condensates can be more simply treated by a semi-classical model because of the three-dimensional constrained motion of 4D and 4 electrons. So 4, this is deuterons, the actual, not deuterium, but the actual nuclei of a deuteron is 4D, little d. And this will be important when we look at the Matsumoto work. And 4e particles in the tetrahedral symmetric condensate into the central focal point. Every QM particle center in the tetrahedral symmetrical condensate can undergo a central squeezing motion with the same velocity to keep charge neutrality. This is important of the total TSC system. In other words, to satisfy the minimum system energy state, what is that? That's a sphere. As calculated by the variational principle of quantum mechanics, QM. Therefore, this squeezing motion can be treated approximately by Newtonian mechanics until the point at which 4 deuterons get into the range of about 5 femtometers of the strong nuclear interaction. So this is effectively self-compression. Self-compression until the deuterons are close enough such that the strong force takes over and they just snap together. Okay. TSC, tetrahedral symmetrical condensate, squeezes from about 100 picometer size to its minimum size of about 10 to 20 femtometer diameter and behaves as a charge-neutral pseudo-particle. Charge-neutral pseudo-particle. What does that mean? That means it's a quad neutron. And what did you have on the cover of the book by Takaaki Matsumoto in 1990? Well, you have mini-band, gravity decay of quad neutron. Gravity decay of quad neutron. There we go. TSC squeezes from about 100 picometer size to its minimum size of about 10 to 20 femtometer diameter and behaves as a charge-neutral pseudo-particle. The lifetime of the TSC is estimated at the time difference from 100 picometer size to the minimum size with a velocity of the order of 10 to the 5 centimeters per second. We obtain about 60 femtoseconds. This was later found to be much shorter of 1.2 femtosecond. What is a femtosecond? It's a really small amount of time. I've never checked this, but I was told by Professor Francesco Piantelli that a femtosecond is about the time it takes for light to travel across the nucleus of a hydrogen atom. So you can imagine it's not a very long time. It's quick. If you want to know why hydrogen bombs go bang and they fill a large volume very, very quickly, it's because these kind of nuclear reactions, when they actually happen very, very quickly. Okay, so here we have a scenario where you have the 1, 2, 3, 4 deuterons. They're all coming from the O sites to the tetrahedral site, and you have the spin up, the spin down, the spin up, and the spin down, forming 2 Cooper pairs, which form a condensate. That forms your sort of basically a big S shell around the whole lot that does self-compression, and that forms here into the minimum tetrahedral symmetric condensate. And you have somehow 2 of the atoms here, nuclei rather, they go from being well, you basically have 4 deuterons. So in this case, it produces 8 beryllium. And 8 beryllium doesn't like to hang around very long. It breaks up into 2, 4 helium. So that is what they are saying in this case. So schematic of a 4D TSC condensation, TSC, T naught, blah, blah, blah. The intermediate excited nucleus is the 8 beryllium, and 8 beryllium undergoes final state interaction to break up. Okay. Now the interesting thing here is a lot of people will know about muons, and this is the first time that I have seen this laid out, and it's the first time I've ever heard it discussed in all my time in Lena. is the screen energies for various EQPET molecules. Okay, so you have your normal electron here, and that has the screening energy of not a lot, right? A Cooper pair has a screening energy of quite a bit, right? And in the case of a quadruplet, you have 4,000 here. And in the case of an octuple coupling, you have screening energy 22,154. Now look, that is like 3 times bigger, or roughly getting on for 3 times bigger than you get with a muon. That is massive. And look at here, the picometers, the distance of your deuterium with this electron condensate. Remember, the E star is whatever the electron condensate is. In this case, it's a normal electron, so it's not a lot. With a Cooper pair, it's actually 10 times smaller. With a quadruplet, it's another order of magnitude smaller. But then it starts to get, interesting down here, because this is twice the distance, or less than twice the distance of the muon, which achieves room temperature fusion and can catalyze that to go on to other reactions. And in this case, this is well below. This is like less than half of the distance. So if this happens at room temperature, this will happen much less than room temperature. Okay? So this for me is very, very interesting table. This explains for sure that I was right in my hunch when I looked at the patents and it said that they were looking at heavy electrons. And Ken Shoulders was saying that, basically a Cooper pair is just two normal electrons. It's just a group of electrons. And a muon is like, in this case, 208 electrons. So what Ken Shoulders is saying, and I'm going to go a little bit off what I wanted to say here, but I want to say this now. What Ken Shoulders is saying in his 2010 interview with John Hutchison is that an exotic vacuum object is effectively just a cluster of electrons. In the same way, he said this, as a Cooper pair is 2, and a muon is 207, or whatever, 208 mass. A tauon, I'll get this wrong, but it's something like, it's in the multiple thousands, I don't know, 3,700 or something. But he says he can get them into the hundreds of billions worth. Now, if you can imagine that you have a scenario where a electron condensate can self-collapse 4 deuterons into 8 beryllium, and that decays to 4 helium. You can then imagine that an exotic vacuum object where you have coherent electron sheath having captured matter, when that gets to a certain level of intensity, it self-collapses and you get much heavier elements. This, in my view, would help us get to a deep understanding of how John Hutchison can have spheres removed from the center of his experiments, and how also we have observed these same things in Vega experiments, and how also Matsumoto observed in his research in the early 1990s, where he would get spherical-like structures being eaten away at grain boundaries. These spherical-like structures eaten away. And he ultimately concluded that these were itonic clusters, and we'll talk a little bit about those. And that here we go, on the crystal grain boundaries. I've shown this before. So you've got these little spherical things that eat away and end up eating the crystal grain. So, and we've shown that these kind of spheroid-type, crystal-type structures can eat material in the Vega experiments, and that they are a micro version of what we're creating on the anode in macro form, and that you get these little hemispheres forming on the outside, but if they get big enough, they all wet into one sphere, and if that gets intense enough, it will eat anything. It will literally eat anything. And so the fact that John Hutchison is observing the synthesis of heavier elements and the disappearance of matter, and that will be important when we look in a minute at the 1990 paper of Takaaki Matsumoto. The fact that he observes disappearance of matter from inside the center, as Matsumoto did, as it would appear we have, then I believe it is to do with electron condensates, and those are what are causing the process. And I can only conclude that Shoulders is absolutely correct. That's just it. It's just absolutely correct. And it's kind of like, it's kind of trying to pretend that Shoulders didn't have it by kind of like, you know, oh look, we can get Cooper pairs to join together. Yes, you can. Okay. So palladium lattice in face center cubic lattice. So yes, it's the same with nickel. It's face center cubic lattice. Only 4 deuterons or hydrogen, TSC, can condensate ultimately to a final very small charge neutral entity. Charge neutral entity, well, if you've got 4H and you've got a charge neutral entity that's made up of 4 electrons and 4 protons, and it's charge neutral, what do you have? You have a quad neutron, just as Matsumoto said. Okay. Blah 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 blah. Entity with about 10 to 20 femtometer radius at the final stage of 4D TSC condensation, about 2 times 10 to the minus 20 seconds. There's your small femtoseconds. 2 times 10 to the minus 20 seconds. Yeah. Try and get a stopwatch to measure that. 4D fusion with 2 4-helium products takes place with almost 100% probability. Okay. I'm going to read this section in a minute because it's some advice for researchers. We find that 4DH TSC can condensate ultimately to a very small charge-neutral entity and has no stable or ground state. This may be the reason why we do not observe D4 molecules in nature. On the contrary, 3D+, which is effectively lithium molecule, and 6D+, it's kind of like carbon, molecules have stable ground states. Equation 13 was numerically solved by blah, blah, blah. Blah, blah, blah. The ultimate condensation is possible only when double platonic symmetry, 4D TSE, is kept in its dynamic motion. A sufficient increase and superscreening of the barrier factor is also only possible as far as the platonic symmetric 4D TSE system is kept. Therefore, there should always be 4 deuterons in the barrier penetration and the fusion process, so that the 4D simultaneous fusion should take place predominantly. The portion of the 2 blah 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 typical nuclear products of 4D fusion, for deuteron fusion, are naively predicted to be 23.8 mega electron volt alpha particles. So you can have alpha conjugate nuclei because these are interacting with nuclei around them. There may be dominant outgoing channels via excited states of fragmented composite particles such as 4 helium and 6 lithium, which produce 4 helium particles, alpha particles, mostly in the 2 to 5 mega electron volt. Blah 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 blah. I think that's what I want to get out of there. I just want to, whether I want to read this at this moment, maybe I do. Okay. Is it going to let me? Okay. I'm going to, maybe I can edit it here. Is it going to let me do it? Okay. No. Okay. So I've said several things here which I want to talk about. And I'm going to, maybe you can see it. I don't know. Here. It's not very big. So charge neutral entity, in the case of 4H, that is a quad neutron. Matsumoto said in 1990 that there was self-collapse of quad neutrons, which is 4H charge neutral entity. Now, it was much later in the 1990s that he realized the vast numbers of nucleons in ball lightning structure, and only in 2001 did he concede that what he had seen in his NATO structures was something similar to EVOs. Roger Stringham, if you remember, Roger Stringham had the collapse of electron condensate around a deuteron condensate at resonant nodes. So here we are back to ultra. He's saying at the resonant nodes you get charge separation. If you've got deuterium in your interacting with your metal, you have the resonant nodes on there. They cause charge separation. You end up with the Cooper pairs forming into an electron condensate sphere. around deuterons inside. That gets to a level of intensity, and then you get a self-compression process, and then you get fusion. And in the case of Adamenko and Vysotsky, they have a lattice arrangement. And if you go and look at their 2003 paper on how it works, they talk about the electron beam coming into the metal. It forms this Wiglet cell or whatever it is, I can't remember. You can go and have a look at my presentation on that. But it forms this cell that gets to a level of intensity, and it self-collapses into an electron nucleus condensate. So electronuclear condensate. So basically, it loses its definition of what it is, and this is more in line with the later thinking of Matsumoto, which actually predated that paper by Vysotsky and Adamenko. But whatever. It is focusing on getting a lot of electrons into Cooper pairs, and then the Cooper pairs becoming a Bose-Einstein condensate, which is a single macro, effectively like a heavy electron. It's a heavy electron. So when you see that ball lightning in the Vega experiment, it cut the tungsten wire when it gets energized enough, and it falls down, and as it's falling down, it stays on the wire, but it orients the wire to the magnetic pole of the other ball lightning there. That is what I have in my head, that the entire ball lightning is acting like a macronuclear object. It's like one S shell around whatever's on the inside of that S shell structure. It's like one charge. Ken Shoulder says you can take it from like 100 billion all the way down to one charge. And effectively, it's just a whole bunch of electrons that are in the same phase, and they are at the same energy. They are a coherent state. And when they come back into the normal electron world, all the energy they gave up, they have to get back. And they have a Coulombic explosion because they present their charge, and then they want to get apart from each other. And that is what you see, my dear friends, in the very first video I shared from Vega experiments called Evo Blaster. That is what you see. You see a black Evo that probably only has a one charge, or is basically charge neutral. It hits the cathode, it gets excited, and then it explodes. And you get this cold patch on the iron of the reactor, as it instantly cools, probably down to minus 273 Kelvin, or 0.1 or 2 or whatever it is. And it sucks the energy instantaneously out of that iron, and that is gaining the thermal energy that was lost when the condensate formed, i.e., when you go from plasma to gas, you have to give up some thermal energy. You go from gas to liquid, you have to give up some thermal energy. When you go from liquid to solid, you have to give up some thermal energy. We go from solid to condensate. In the electron condensate, you have to give up some thermal energy. And it gains that back. They become normal electrons again, and they want to repel from each other, and so you get those little explosions. And because they are charges moving in a spherical vector away from a central point, you get a scalar pulse. You get a scalar wave coming out of that. Anyway, there we go. Ta-da. Right, so how are we doing, guys? How are we going? So yes, it's an implosion process, and it's kind of like dual implosion. You've got the self-compression of the electron condensate to a point at which the strong force takes over with the nuclei that are within inside that, and then the strong force takes over, and you get nuclear reactions. And in part, if you have this electron condensate around the outside, if any gamma rays or whatever are produced, they go out. And I've only literally found that Preparata said this exact model for explaining why there are no photon emissions normally in LENR, is that the electron condensate captures the emitted photons or whatever they are, and it just distributes it among the population of the electrons. So if you've got 100 billion of them, that's quite a few to distribute among. If you've got 10 to the 23, that's a lot. It's just a lot to distribute them between. Okay, so this is the point where I need to go to the last reference that I have here. Thank you, Magic Sound. So I think this is important for you. And in fact, at this point, Alan, I'm going to talk about Brillouin because, as I said, I haven't always agreed with the explanation for that. In the case of Brillouin, they've got some nickel. It is whatever structure it is. It doesn't really matter. They are loading it with their hydrogen. So it's basically the same thing as you're observing here. In the case of these guys, they're using thin film. And what they're doing is they're doing a Q, what he calls a Q pulse, which is a very, very fast DIDT pulse going through that metal lattice. And that produces a Brillouin wave, hence the name. And that causes these vibration. And this is like that 2014 video I shared of my darling wife hitting a Tibetan singing bowl, and you get a resonance there. The kind of way that I'm talking about by using microwaves and a transduction piezoelectric material is to do the gentle vibration at the resonant frequency. And this is what I propose Brillouin add to their system to make it more predictable and controllable. Norris Perry spent his entire research for 20 years or something trying to get faster and faster and faster pulses. At some point, he ended up by not being able to get a fast enough pulse. And so it was suggested by the electric engineer, well, we can go to microwaves. Okay, and of course, John was doing that in 1979. So anyway, he's way ahead of everyone. But anyway, the point is, Norris Perry realized this. And I'm suggesting that in the case of Brillouin, they could consider doing actually what is in Celani wire. And in Celani wire, he creates the wire which is copper and nickel. It's got a much lower copper ratio than is in this one here. I think this is just 2 nanometers and 16 nanometers, but in his it's like a 60-40 ratio. So it's a much higher ratio rather of copper to nickel. But it doesn't matter. He dual heats that to oxidize it, and then oxidize it, and it produces these nanostructures that he then reduces with the hydrogen to produce these nickel nanostructures in this copper lattice. But it's on a substrate of this Constantan wire, which then allows you to directly heat the substrate from the inside. So it's absolutely wonderful, and that also creates a magnetic field because it's a wire, right? So you've got a lot of things that you can control with this. What he also does is he coats it with sol gel, and sol gel then becomes silicon dioxide, and silicon dioxide, as we know, is piezoelectric. Okay, now why would that be useful? That would be useful because you could use a magnetron and you could excite that silicon dioxide, that quartz, that piezo structure that is within this hydrogen-loaded nickel to produce gigahertz phonons directly in pulses. I think this could be a way of combining what I suspect is going on in John Hutchison's material and what is also going on in the Salvatore Pais patterns, which were published after I suggested this. But by the way, the work was done in the 1950s and published in New Sciences in the 1963 to improve the Celani wire process. And I think the same thing could be applied to Brillouin devices. They could coat it, and as I'm giving this out so everyone can use it for free, okay? Brillouin could do sol gel process similar to what Francesco Celani is using to allow for some production of quartz nanocrystals on there. Or you could use, I don't know how you would get it on there, maybe sputter or something and oxidize. You could use zinc oxide. Zinc oxide obviously has a melting point in the high 1000 degrees, so 1700, 1800, I don't know, 1900. It's high, okay? So it's well beyond the melting point of nickel, and it's well beyond the melting point of copper. So I think this would also be suitable, and it is also thermoelectric as well, which is just interesting. But it's piezoelectric, so you could use zinc oxide, or you could use silicon dioxide on there. I think zinc oxide has the higher melting point. And so put that on there, and then you could use electromagnetic waves to stimulate the phonons directly at a higher pulse shock rate than I think you could achieve with any pulsed electronics. Anyway, that was the conclusion that Norris Peary came to, and I think this is a mechanism by which you could have more transduction of the electromagnetic waves into phonons within the metal lattice. And it specifically says, as I said earlier, that in the 1963 paper, that this gave them a means to vibrate metal lattices at the inter-lattice atom distances. So what you need to think about that is you've seen our ultra experiments, and what was being used by what's his name? Oh God, I can't remember now. Tom Claytor and Stringham. Tom Claytor Roger Stringham was using ultrasonics in the 20 to 43, like the one we've got, kilohertz for most of his time. But very much more recently, he said that he is using with Tom Claytor, I think around 1.7 megahertz, and that gave many more of these resonant nodes. Now we've identified them in a fixed lattice as being these figures of 8, where you get these maximum deviations. They're in my view the equivalent of the anharmonic oscillations. But in a metal lattice, in a 3D structure, you want to create these things in the same way that Cardone is doing with a sonotrode in mercury. Okay, there's no hydrogen involved there. So we already know that not only has John Hutchison created transmutation in systems that do not include hydrogen, Cardone has done that in a sonotrode, an aluminium sonotrode in mercury. So we know that hydrogen is not necessary. The important thing is coherent electrons, okay, which is an exotic vacuum object, okay? It's a strong electron, EV, okay? And that clusters the material together into a high-density charge cluster that can get into a neutral state and then go into a point where it's not just electrons and neutrons, it actually is more, it's an exotic vacuum object, okay? So they're going to 1.7 megahertz. Now, what I'm talking about is 10 gigahertz. I'm talking about, I think what did John Hutchison call it? 100 kilo megacycles or something. And maybe that's not the right frequency, but anyway, you can get much higher with this and be able to control it with very, very discrete pulses. So yeah, that's basically my suggestion before we look at Matsumoto's paper here, which is observation of new particles emitted during cold fusion technology. And for me, Takaaki Matsumoto has actually a more full explanation, and I think people will come to appreciate his work. And I think what people should appreciate most about Takaaki Matsumoto is that he started off with an idea which kind of worked, but when he observed the experimental data, the bits of material disappearing inside his deuterated palladium lattice, when he observed that, and he observed that it was these circles, why would the circle occur? Why would circles merge into a big circle? Where was the matter going? It had to have been converting into something that could leave the center of a piece of material, just like as observed in 1979 by John Hutchison and beyond. So he actually kept thinking. And at the end of the day, in 2001, I think it was, he suggested that to create these itonic clusters, you use electron bunching, which forces them to cohere, which forces them to form Cooper pairs and electron condensates, and then have protons coming in, which are coming from a linear accelerator, into that electron condensate, and that would form itonic clusters, which also include nucleons. And then in his conclusion to his work, he says, it doesn't matter what you put in, it'll do whatever with whatever, and mostly it ends up producing carbon. Okay, so I want to close out with this. It's a fairly short paper. But I think it's important to do this. I've actually got it here. Matsumoto 1990. This is from Fusion Technology, when they allowed him to publish before they changed the rules. So it was received March 26th, 1990. So to confirm the emission of iton particles predicted by the NATO model, a cold fusion experiment based on electrolysis of heavy water has been performed. The tracks of several kinds of itons have been successfully recorded on nuclear films. The formation and decay of mechanism of itons are included in the NATO model. So I think I first mentioned what a NATO model actually was by, I think, the 2003 or 2006 paper I recently went over from Savatimova and her colleague when explaining the work of Iwamura in this calcium oxide and palladium and deuterium system. But so here, results and discussions. In a forthcoming paper, and that, by the way, that was with the dineutrons, and we're going to see dineutrons here, and we're going to have to consider what we are learning from this. So, results and discussions. You can't see what I'm looking at here. I'm looking at this paper here, so you can go and download this. Observation of new particles emitted during cold fusion from March the 26th, 1990. Published May 1990. Okay, so results and discussions. I'm going to go here, and I'm going to go there, and I'm going to go pull that over there. Okay. In a forthcoming paper, we describe how we predicted the emissions of itons, as well as the mechanisms for formation of the natto. Natto is a dough ball in Japanese, and so he's saying that something forms, which is like a dough ball, and inside there, then the nuclear reactions occur. And I agree with him when the natto is formed. Electrons connecting hydrogens are also pressed extremely close to the hydrogen nuclei. In the hydrogen nucleus, the depolarization takes place. The hydrogen nucleus, the depolarization takes place by inverse beta decay. So the proton goes to a neutron plus a positron and a neutrino. So the electrons that are joining these hydrogens together, like you saw in the TSC model, they're compressing together, and it polarizes the proton to a point of it actually becomes a neutron, releases a positron and a neutrino. And so this is inverse beta decay. And who else do we know does inverse beta decay? Well, none other than our friend Alexander Parkhomov. There we go. So there's your inverse beta decay. A dipole layer consisting of an electron and a positron is formed. Receiving the quantized excitation energy of the fusion nucleus, the iton is emitted as thus. So, you have an electron coming in, which is doing the polarization as part of the cluster of electrons. It produces a positron here and a neutrino. And all three of these things become a clustered structure, which is a electron and a positron and a neutrino. And that, my friends, is a single iton. Okay? It is assumed that a neutrino, V, is also contained in the iton because no gamma rays are observed due to the annihilation of the electron and positron pair. So the reason you don't see gamma is, according to Takaaki Matsumoto, is that the formation of the iton stops the two 511 keV 180 degrees flying gamma rays coming out, because it forms into this particle. Because no gamma rays are observed due to the annihilation of the electron and positron pair. So they don't annihilate, they form this particle called the iton. Okay. Of course, this particle is unstable, so that it decays in the inverse direction of equation 2. So it actually goes back to, at some point, an electron, a neutrino, an electron, and a positron. Moreover, if two electrons are pressed into the fused nucleus, a double iton is formed as follows. 2 electrons plus 2 positrons and 2 neutrinos form an I2. And there you go. It's got this symmetrical structure here. Although the double iton eventually decays into 2 electron and 2 positron pairs, it can decay in various ways. For example, blah, 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 to all these different ways. There we go. Okay, so this figure 1 shows all of the possible decays. I haven't quite worked out what this means, but there we go. And he observes them, apparently. Many tracks were recorded. Okay, you can go and have a look at this in your own time. I want to talk about the actual proposed reactions down here because we're going to recognize a few of them. Right. Now we can see the emission of itons during the hydrogen catalyzed fusion reaction. The fusion products must be modified on the NATO model. When a single iton is emitted, one of the two fused hydrogen nuclei is fermented. So you have two deuterons and an electron plus an extra deuteron goes to quadronium plus an iton plus a deuteron nucleus. Okay? What does this go to then? The quadronium goes to 4 helium plus an electron and an antineutrino. Okay? Why is this important? This is important because this here, this is what is claimed to be occurring by Brillouin. In fact, Brillouin are saying a proton does an electron capture. That makes a neutron, and with another proton, that makes a deuteron. And with another proton that does an electron capture, you have a triton. And then you have another proton that does an electron capture, and then that produces quadronium, and then that decays very, very quickly to 4 helium plus an electron plus, in this case, but it decays like that. So the problem is that Piantelli said this is absolutely impossible. You just can't happen. You can't just get an electron going into a proton. It just won't happen. You have to have a scenario which is something like the TSC proposed and used by, basically, it would seem, all of the Japanese community. And that is actually very similar to what is being proposed here by Matsumoto in, I think it was in 1989, but this is published in 1990, the beginning of 1990. And so I think this is probably something like what is going on in the face-centered cubic lattice of the Brillouin system. That it isn't this stepwise process, it is a symmetrical collapse, as is said in the TSC, and it goes through this kind of process. It's as far as I'm concerned, this is pretty much what's going on. Okay, so they have another thing over here, a couple of other reactions. So connection, blah, 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 blah. On the other hand, for the double iton, so we've got a double iton here. If you have 2 deuterons plus 2 electrons plus a deuteron, and they come together and you have, this is a quad neutron plus a dual iton and a deuterium nuclei. It can either do that, or it can go to quadronium, which decays, as we've seen, a dual iton and 2 neutrons. What is this? This is a dineutron. This is a dineutron. Okay? This is this thing that has 22 mega electron volts, according to Savatomova and the Russians in the Barut model. And that this dineutron has a higher binding energy than even nickel 62. Quite a lot higher than nickel 62. I think it's 11 per neutron in the dineutron. And that is, what is it? It is a Cooper pair in the center, superconducting, and then it has 2 protons on the outside. That's the kind of like a dineutron. Okay. Where Kn is the neutron nucleus consisting of K neutrons. So it actually may be more neutrons. The beta decay of 4 quadronium could be confused with the beta decay of tritium. Okay, so saying you might see this as thinking that the decay is of tritium, but it's actually of quadronium. Okay, produced by the conventional DD reaction. Here, the neutron nuclear can be considered to decay as followed. The quad neutron decays to quadronium plus an electron plus an antineutrino, and that can further decays to 4 helium plus 2 electrons plus 2 antineutrinos. The remaining dineutron decays to deuterium plus an electron plus an antineutrino. And there you go. Everything's kind of tied together there. And they've got one more thing down here. You can have alternative by gravity decay, which is the basis of what he has on the front cover of his book. It's a quad neutron to neutrinos and antineutrinos, and dineutron to neutrinos and antineutrinos. Okay? So these are micro chargeless leptons. And so this is what I'm saying, is that you can have, you missed that, it's here. the quad neutron to neutrinos and antineutrinos, and dineutron to neutrinos and antineutrinos. So this is what I'm saying, is that the collapse of matter could lead to the production of leptons, and both charged and uncharged. And that's it. That's where the matter disappears. If it comes out as a whole bunch of neutrinos as microleptons, it's basically gone. That's it. That's why you got nothing there. Right. So now the question is that if you have this large electron condensate, so Matsumoto was saying this in late 1989 into 1990, but as he got to around about 2000 the end of 2003. He was listening to the ideas around micro ball lightning, and that was before he really connected it to shoulders, and that was the time that he was cut off. And at that time, that was when the US Air Force, I think it was, that stepped in and said, look, if we can create a synthetic ball lightning structure, this will do fusion, and it will self-confine, and you'll be able to feed it matter, and it will do fusion. And they said, since we know ball lightning has been observed in the 10 millimeter range, we should be able to generate reactors that have things that are scale of 10 millimeter. We have observed, Matsumoto has observed, John Hutchison has observed, Ken Shoulders has observed, and many authors have observed structures that are much smaller than 10 millimeters, and therefore we can, in theory, produce these things vastly, vastly smaller that will be able to do fusion through the self-confining process of coherent nuclear condensates, including, and most importantly, the electron condensates that form the exotic vacuum object skin. There we go. And you can make matter disappear, and that's it. You can make matter disappear. And you can also use these things to condense matter by capturing cold neutrinos from the cosmos. So, are there any questions? How can we help make that happen? Well, I'm going to be writing to Matsumoto again, and my facilitator show in Japan is going to help that. And at the moment, there's no one recognizing natural immunity, and until that happens, I'm not going to be able to travel. But there is some legal moves being made in the States, and since everyone seems to follow them, hopefully that will change perceptions on immunity. Then I will be able to travel. But we have a backup plan, and show will go to him, and then we'll do some. He will take a computer, because he doesn't have a computer, and we will do discussions and interviews. But I think Matsumoto, to his great credit, did not stay with the same idea from beginning to end. He took on board what he observed in actual real experiments, and took on board what other people were observing. And as I said, in 2001, he conceded that probably what he saw in the itons, it's still the itons, but that they are functionally equivalent to Messiat's ectons and Ken Shoulders' exotic vacuum objects, where we have been able to add to that is to show that we've actually visualized how these things are clustering on a macro level, and how they're clustering on a micro level, and how they are consuming matter. And we've added layers of data to what was already shared in this book, in the papers, predominantly published up to 1995. Okay, so I'm going to see if you've got any questions. What impact is the atmosphere able to help solidify the bubble of ball lightning? So if you go and look at my review of that 1995 published, but December 1993 submitted paper by the Air Force to, I think it's by Roth, to fusion technology. They are talking about nitric oxide formed within lightning and in atmospheric energetic events being an assistant to the formation and stabilization of ball lightning. So we nitric oxide so corrosive, we were going to get some, but it was ridiculously expensive. So we've got a different gas that has a similar, if not better, profile, and actually has fluorine in it as well. So we'll be able to track transmutations based off alpha conjugates of fluorine. So it's any face center cubic metal that is able to store a lot of hydrogen. Nickel's not that good, actually. It absorbs nitrogen. It doesn't absorb, so it goes onto the surface. And I've argued that actually a lot of this process is to do with getting to coherence, and the way you get to coherence is to get everything exactly the same temperature, and you have something magnetic in the case of nickel, and in both of the materials used by clean in their what do you call it, quantum energy process by Clean Planet. In both of their systems, they're either using palladium and nickel or copper and nickel is obviously the most desirable. But in both cases, they have nickel. That's ferromagnetic. It has this 363 degrees or whatever it is Curie point degrees centigrade. So you get all your material just below that, and this was taught to us by Piantelli, and then you smash through that Curie point as fast as possible. And what that does is your electrons have a little dipole, and your protons have a little dipole, and they get locked into the lattice, and then what you're doing is you're releasing them all at exactly the same energy in phase, and so you get a greater chance of coherence going on, in my view. Tetrahedral symmetric condensates, need to keep repeating this. Yes. It's not so catchy, but the point is that I think the problems that they're having are the problems that all LENR researchers will have, is that you've got a limitation on the Curie point of the material, on the hydrogen storage point of the material, and on the nanostructures of the material. That you need nanostructures because they maximize the hydrogen absorption, they maximize the anharmonic oscillations, and these weird band gap properties that you have. But they also restrict your temperatures because they're more prone to causing sintering and failure of the material. Now that can be an advantage if you don't want them to melt away, but actually what you really need to do, and it was identified by the Roth paper in 1993, you have to use free-floating fireballs. You have to use the natural ball lightning, because what will happen, as we've observed in Vega, as Matsumoto observed in whenever it was when he published that one with the holes in it, I think it was 91 or 90, very early, it will always destroy your reactor, and I fear that that's what will happen to the Clean Planet group, and ultimately we're going to have to get to a point where we control and hold the ball lightning, and maybe we make and break it and make and break it and make it and break it, and there will be a period where the structure is not stable, and in that destabilization phase you will get some transmutation products which might lead to little pulses of radiation, and so maybe you can just bleed it. And the other process is to bleed it, so you just have to feed it and bleed it and feed it and bleed it. This is the biggest challenge. So I think that their runaways is when you're going to get more coherence going on. You're not just dealing with a octet 8 electrons in a condensate. You're going to be dealing with vast numbers of electrons in condensates, and then it just eats a chunk of your material. And I think probably in some of the devices that they've seen these increases in excess heat, if they really looked at it, they would see similar observations to John Hutchison from 1979, from 1989 from Matsumoto, and in the last year or so from ourselves in Vega experiments. They're down to single-digit nanoseconds and many hundreds of amperes. Yeah, but my view on that, Alan, is you are still having to smack it with a hammer. It's not necessarily running at resonance, and maybe they can run at resonance, but it's also the fact that you could use pulses of microwave and have a lot more control. I don't know. I mean, in both senses, you're getting control. So yeah, I mean, it's maybe just another approach. Whether the electronics are complicated, I don't know, but obviously magnetron electronics are not that complicated. You can go out and buy a microwave for like $30 or something, $40. Felix, a magnetic confinement field. I think you need to rely partly on. I think Shoulders used a penning trap. I think in the Roth paper that I think they were suggesting the use of some Helmholtz coils and one of these normal magnetic confinement structures, but you're working with the natural confinement of the ball lining structure. I think actually by configuring your electrodes correctly and by controlling your input power and your gas environment in many ways that were described by Paul Collock in his 1973 patent, I think, for Plasmax and subsequent work. I think you can get to a fairly comfortable situation, and I think that's what we're going to be discussing in Something Electric Part 2. And by the way, that feeds into the propulsion side of this technology. And when it's very difficult for me not to talk about how you create a free floating fireball that you're able to control and generate electricity directly from and power directly from, and not reveal how the propulsion works. So they're kind of going to come simultaneously, and I don't quite know how that's going to happen, but there's a lot of work to do. And I need to try and write my papers for the Azizi conference, and obviously more work on the fixing Fukushima work. But I can say today that if I can find it, I was invited to speak at where is it? I was invited to speak, if it's going to work, talk amongst yourselves. Where are we? So I was invited to speak just before I came over here by Tim Ventura at the Apex meeting on November the 27th. And so, because they are to do with propulsion, if I can find the time and the energy, I will potentially talk about the basics of how the propulsion works. And I think it's pretty much off to the races when that happens. I just like to see what the world does with it. But yeah, I mean, I don't know. It depends whether I can get that out there, but I need more people to be looking at the energy side of this and the fixing the Fukushima, and they have a reach of about 120,000 subscribers across 3 YouTube channels, he's saying. So I think it would be well worth trying to introduce some to our community. I rather like our very small community here, but like I say, I can't really talk about Something Electric Part 2 without really revealing to those people that are able to use their brain a little bit how the propulsion works. So yes, so Gordon, yes, that's superconductivity. It's superconducting, and yeah, it's a condensate. It's superconducting. The Curie point is where the nickel loses its ferromagnetic nature. So if you've got something sitting on, I've got an experiment. I've had all the materials for about definitely 2 years, maybe 3 years in the other room. I might do that in the next couple of weeks. It's a visual experiment, and it'll just be obvious to people what's going on. It'll just be completely obvious, and you go, oh yeah, that's how it works. You'll never need to think about it again. Sorry. What effect is John's effect have on his transmutation? What effect is John's... John is effectively creating resonant nodes in his material. They are creating electron condensates, which are exotic vacuum objects in there. And they are leading to the formation of effectively charged of polar suppressed poles alternately, in the form of pseudomagnetic monopoles, and they are causing the collapse of matter. And in fact, you can think of this self-compression almost as a kind of like it's moving inwards. I mean, it's all moving inwards. So yeah, it's not really monopoles. It's something that's a magnetic arrangement of material that ends up expressing itself as more a focused beam of one pole, as it were. And when you get two of these, they end up creating these flux loops. You see them on the sun as well. They call them solar prominences. Anyway. Okay. Yes, Gordon's got that right when he's describing to Paul Newman. Yes, you get intense phonons from magnetorestriction. Yeah, yeah. Thank you, Alan, for that. It's still, I kind of like, if you go back to that 2014 video I shared of my wife and the person in the shop either hitting a singing bowl or just rubbing it, you know, the rubbing is providing an even energy over the whole thing, and that's what you're getting with an electromagnetic wave. You're able to bathe the thing in the exact frequency that it needs to act with, and so Q pulse is a good phrase because you're implying that there's a high Q in terms of the resonance with the effect that you're trying to create. But in this respect, you should be able to create a pulse, but the actual bathed in EMF should be able to transduce to via the piezoelectric material to exactly the phonons, but starting in many locations rather than from where you are attaching your electrodes. But I mean, it depends whether you've got like a concentric cylinders and you've got an inside and outside. You could do it that way, but there are always ways around these things. So I'm just looking at the questions for people wanting to know why I'm going quiet. If you have any questions you've asked before and you want to ask them again, probably do that. I'll catch them down the bottom. So Gordon Doherty, so the phonon frequency should ideally match the distance between the atoms in the nickel framework. Well, actually, if Brillouin have named their company very well, because it's like, I think it's the maximum wave that a lattice can support. So if you're going to excite it, you're going to want to hit it at the Brillouin frequency. But anyway, you can go and look at that up on Wikipedia in case I haven't got it quite right. But anyway, Professor Francesco Piantelli identified was the fact if you had a nanostructure between a certain number of clusters atoms and a certain other number of atoms, that this would produce anharmonic oscillations on there, and you then get these extreme from steady state departures. And in fact, he described it such that when you have an atom in free space, like as a gas, it has its electron bands like very far apart or whatever, and it can capture an electron or whatever if it's ionized. When you get some of these electrons, these atoms in the outer part of the lattice displaced by these anharmonic oscillations so far, you get a separation between the electron and the conduction band such that it can grab, in his mind, this Cooper pair and a proton, this H minus, and grab it into the nucleus, and it then falls down and goes towards the nucleus. I don't know. It's a whole different understanding, and it's something where I have to imagine it occurring. Whereas what I see in John Hutchison's material and what I see in the material that he has shared and what I see in the Vega experiments is something that you can physically repeat, and it happens every time, and we can demonstrate it on the macro scale on the actual cathodes, and you see the same observation on the very, very small micro level. And so it's working on all scales, and you can see it in less variation, but you can also see it in the Sapphire experiments, and you can see some things happening on a cosmic level, the same kind of processes. So I like things that I can see and that are repeatable. I can't imagine what something is doing when it's falling through electron shells in an atom. Well, there you go. I calculated the primary mode 1 microwave resonance of the hot tube is 11.2 gigahertz. Well, there you go. So you should be able to create a magnetron that's able to do that. And I would suggest adding zinc oxide or silicon dioxide via sol gel, probably the same process that Francesco Celani is using. That may be the easiest. And create little crystals all over there, and then you just hit it with pulses of microwave. And of course you can switch the magnetron off very, very fast, and then the actual pulse is at the gigahertz. So I think if you go and listen to the Norris Peary interview, I think he says I think it was something like 8 microseconds. If he went any further, if he held the pulse for any longer than 8 microseconds, the whole reactor failed. So it was such high Q. Let's put it that way. It was literally instantly resonant with the whole structure. Could this same process be used to make holographic objects? I'm sure it probably could be, but it's not something I've thought about. So if I understand correctly, a system like this can be controlled and sustained for hours, days and months. Well, in the case of what they're saying, they're saying that they are able to produce 1 kilowatt, and this is the report that was given last week, as I understand it, to the ARPA-E meeting. And they've been able to sustain that for about 3 months, so it's 120 days, right? 4 months, that's 4 months, isn't it? In the case of Parkhomov, he sustained for 225 days, so that's 7 months. Much more simple thing to create is industrial PNKO2 nickel, carbonyl nickel produced in Russia. And this is degassed and heated and then loaded with hydrogen. That is slowly heated up. Effectively, the same protocol as we shared as part of our Alan Goldwater's glow stick 5.2, but the process that we developed from taking some learning from previous Parkhomov experiments and the teachings that we had from Francesco Piantelli, combining those and coming up with this protocol that then fed back into the 225-day protocol that was used by Parkhomov and produced this wonderful long-running reactor, which at peak produced I think COP of 3.7 with about a kilowatt in, I think. So it was producing a couple of kilowatts. But that actual period did not last very long, and I think over the 9-month period it was producing, a 7-month period rather, it was producing on average around about 200 watts excess, so about 20% excess over the entire 7 months period. So 4 months at 1,000 watts, 7 months at 200 watts, but perhaps Clean Planet have the crown on the maximum amount of energy produced. But I think Parkhomov had only 2.1 grams of nickel powder, and negligible amounts by weight of hydrogen. Although, as I've said before, I believe that the active agents, the exotic vacuum objects, were synthesized by the nickel. I've explained how that occurs in my view, and that came out, passed through in neutral form into the tungsten heater wire, and the heater wire fissioning probably produced a large portion of the heat. I don't know how long you've been with us, Buster Cap, in your... I'm not going to say the rest of it, but great name there. There's a lot to learn, but fortunately most of the hard work has already been done by people that preceded me, but no one was paying attention, it would appear. For instance, it's only the last few days that I have bothered to read for the first time, and I've been doing this for 10 years, Takahashi's process, and it was just amazing to me, having guessed from the patents without them ever mentioning it that heavy electrons were Cooper pairs that were forming condensates, and that was leading to the fusion. He says it there, right in his work, So it's not a surprise, and it's just wonderful. But for me, it's a bit of a... It's weird. I know everyone wanted to solve it, but I think it's difficult. I think for a lot of people, because obviously Ken Shoulders had already essentially nailed it in the 1980s, based off his studies of John Hutchison's work, and some finer minutiae were delivered by Matsumoto, and then it plays into every system. Every system you look at, it's always going to be doing this. All of them. It's just difficult to absorb heavier gases into these metals. They're just... The nuclei needs to be quite small, otherwise it's just gonna... No, it's not gonna work. But it doesn't matter. When you have a ball lightning, it'll eat anything. Anything you can give it. It doesn't matter if you're feeding unobtainium or, just anything. It'll consume it. Okay, so I'm going to call it a night. It's 00:45 here. Thank you. I'm sorry that I had a problem at the beginning. I don't know what happened, but I'm very thankful the fact that I thought, for whatever reason, I had lost the USBs on this streaming computer, but I haven't. That's a good thing. So thank you very much for your time. This was a review of the materials I believe and concepts that I believe were presented by Clean Planet, and the latest data that was presented by Clean Planet to the ARPA-E group. And you've got all the links already in the presentation header on Remote View. So if you go to Remote View, it's on a free link there. This is the presentation we're recording right now, and you've got the Japanese for those that want to read the original Japanese. Then we have the translation, Japanese translation, the Takahashi thing that was sent to me in October 2021. That was sent to me yesterday, or now 2 days ago, I guess. And this this link below is a link that I found from there, and you find that the same graphic of how the process works is in all of these documents. And so and then I tied that into Matsumoto, and I said that how that would relate back to observations in the ultra experiments, in the Vega experiments, in the work of Brillouin, and basically each of these three people are taking 4 hydrogens and fusing them and getting helium out, and they're coming at it from different angles. I think that the Clean Planet use of Takahashi's process does explain most of the anomalies, but Takahashi is still revising his theory. I think Takaaki Matsumoto pretty much nailed it, and the revisions to his theory, including the realization that this is effectively the equivalent of ball lightning, and that is essentially an exotic vacuum object, and that it is an itonic cluster, and I believe that we have observed itonic clusters in the vibration system, or marks of itonic clusters in the vibration system of Dr. Roishi Namaza, and we have observed them in the inside of the hollow shells where the reactions take place in the Vega experiments. And so I think pretty much Takaaki Matsumoto is on the money, as it were, but it doesn't really matter. They're all moving towards transmutation, but Clean Planet and Brillouin are really only talking about taking hydrogen atoms and using a metal lattice to get them to helium, whereas Takaaki Matsumoto did that, went past that, and realized that you can take any nuclei, and it's vast numbers of nuclei, microns wide, and we've demonstrated that, and that can transmute it, and it transmutes it mostly to carbon, and I believe we've demonstrated that as well. And so I think Takaaki Matsumoto, well done you. So thank you very, very much for your time this evening. It's been a pleasure to be with you, and I will see you in the next stream, which I think, what am I going to talk about in the next stream? I had something, you're going to find out. I can't remember offhand. Anyway, probably on Sunday. Please ask questions if you can in remote view, because you can share links there, and it has persistence. It won't have a problem if YouTube decide too much information and cut the thread. And just again to trailer, on the 27th I will be talking in Tim Ventura's meeting. It will be a Zoom chat, so I'll try and share that as well, but I will also rebroadcast that on my channel. So thank you very much for your time, and I will see you in the next video. Buenas noches, dobro noc, buena notte. Good night.